And one other thing is classification of images. So before people try to, for example, you have pictures, you have many pictures, and you try to teach the computer to learn if there is a count or not a count in a picture. And then this is easy for even a child, 2-year-old or 1-year-old. They already can do this. You just give them like 3 or 4 pictures. And with the deep neural networks, they can do it. Okay, so how? So maybe I just tell a general strategy. This and so it's not represent everything in deep learning, but it's convey some main ideas. So how do we do this? First step is we can collect a big data set, like the picture is the xi, you have picture, and then yi. So now, okay, say you want to see if picture has a dog, cat, or mouse, and you assume that all the pictures you have only one of them, and then now you want to teach the computer to learn. So how? Okay, the first thing is to represent the data x, y, I. One thing you can do is you can use one for the one hot vector. So here you have 3 categories, so dog, cat, and mouse. So you can use a vector with 3 coordinates, and the first coordinate will represent the dog. Second coordinate represent the cat. Third coordinate represent the mouse. And for your data, for your yi, you will say, okay, 1, 0, 0 means that this is a dog, and 0, 1, 0 is a cat, 0, 0, 1 is a mouse. Okay, so this is a way to represent this, and it's a good way to represent this kind of, like, if you have many categories. Yeah. Big enough, it's difficult to say, but maybe for this, maybe some 1,000 pictures or some 10,000 pictures. Yeah, so it may depend on your data. If your data very
there's a piece of
yeah, it depends. Yeah. So it's difficult.
The n is the number of categories.
No, the number of images you have in this case. The categories you have only 3: dog, cat, mouse. You have 3 categories you want to classify, and you have n images. And this of them will be in one of these categories. Now, the second question you can ask is that, now I will try to find some function f like this. That okay, just now I don't care what f is, but what I care is what value should f take. And maybe you can think that, okay, because 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, so the values of f should be only these 3. So just a finite set 1, 0, 0, 0, 1, 0, 0, 0, 1. But if you think about this, then if you only have finite number like this, then it's not good, because then you are working with a discrete set. So it means that you are trying to find out maybe then your function is discrete. That is very difficult, because usually if you have continuous functions, then it's easier to work than discrete functions. So it's better to to assume that fx beta here, assume that you already give a value for beta, then it should be it should take every value, not just 0, 1, 1, 0, 0, 0, 1, 0, or 0, 0, 1. Because then it's very difficult to work. For example, you cannot take derivatives, you cannot you cannot do many things, because many algorithms like gradient and so on, you need the function to be C1 to, or at least you can take derivatives somehow. You don't need a C1, but somehow you should it should not be just decreased, because it's difficult to work with. Yes, so this one I mean, and then so we can assume that ABC can be any number, but we are now what we think about ABC. Okay, we think about A like the property that your picture is dot. B is the property your picture is cut. C is the property your picture is mouse, and A plus B plus C equal 1. For example, if you get the 0.5, 0.4, 0.1, so what does it mean? So you think that this picture has the property of the file text to be a dot, and for text to be a cut, and one of text to be a mouse. So if you need to give only one answer, then you will say that okay, this is the picture of a cut. No, of a dot, because 0.5 the biggest number. Yeah, so this is the another idea. And how can we get this number ABC? How can we be sure that we can get these ABC numbers and they always bigger than 0 and the sum is 1? And one idea is you can use what for the softmax function. Maybe over this. Yeah, softmax function. It's very simple. If you have like in this case you have ABC 3 numbers, then you just take like x, y, z. Then you just take e to the x over ex plus ey plus ez, and then e to the y over ex plus ey plus ez, and then e to the z ex plus ey plus ez. And so you can check that all these numbers are bigger than equal, actually bigger than 0, and the sum is 1. So you can think about like, yeah, so actually it's set here. So here, yeah. Yeah. So there's another idea you can use. Of course, actually whether these numbers actually represent their properties, we don't know. But the experiments, they show that this idea of using softmax function is good. Yeah. So then that's how you do. Then the other thing is you need, like, if you look at this classical statistics problem, you need to measure the difference between your actual value, which is yi, and the value predicted by your function, which is fxi beta. This is called metric, and you need to find an appropriate metric. I will come later, but also for this case where you work with probabilities, then usually it's good that you use the cross entropy, for example. Okay, so any questions? Okay, so if not, I come to the second section, the first part of second section about many fields. Actually, now many fields mathematics they contribute to this deep learning, machine learning. Let me start with logic. Okay, so maybe you can say logic is the foundation mathematics. So if mathematics has the application to deep learning, machine learning, then of course logic also. But actually, the application logic to machine learning, deep learning is more direct, and And so this one is indirect possible if you say like optimization application to machine learning, deep learning, then of course logit also, because logit is up their foundation. But actually it's more direct, and it's crucial to both artificial neural networks and computer science. And to see this, yeah, so this is a quote from a paper I will open now. Actually, the paper I have in the references. Gottfried Leibniz, Bertrand Russell, and Alfred Whitehead. One the best, one and Marcus. The one the best is the one. Yeah, maybe is the main character of this the article. So Leibniz, his idea was that okay, yeah, you can everything in life you can represent it in terms of logic. You can use like that you and or not and so on to represent everything, even life. And then Bertrand Russell and Alfred Whitehead, they wrote a book, very big book about this. And then quantum bits and Warren Marcus. So Warren Marcus, he's a biologist, and then he had this idea, but he's not good in mathematics. So then he worked with this person, quantum bits. And then they kind of had the first ideas about neural networks. Yeah, this is what McCulloch he recognized that a neural signal is like a proposition, and neurons seem to work like logic gates, taking in multiple inputs and producing a single output. So this means that okay, you have many. So maybe you have some neurons in your brain, and they do something, and then they need input. If that input is above a threshold, then they will fire a signal out. If this is less than a threshold, then they not fire anything. So it's like yes or no. So if it's bigger than one value, it's a yes. Smaller than one value, it's no. So then you can represent it in logic, because logic is yes or no, true or false. And actually this, yeah. No, can look at this. Hopefully I can. Maybe okay. I need to copy this. Yeah, so this is a very interesting article. If you are interested in machine learning, deep learning, and actually, I think now with the current status of deep learning, then understanding more about how you can use logic is very crucial, that you can improve the performance of machine learning, deep learning models. So they said methods, and but one thing they said in this is that what they studied about this type of logical logic gates, and then later for von Neumann, he used this in his design of computers. So actually they were before von Neumann, and they developed this for neural networks first, and then after that Neumann, he used it to design his computer. The first maybe not the first, but maybe the first good computer, maybe. Yeah, so this comes from the study of biology and logic. Yeah. And later, I will explain why I think that logic is still important to create two AI, because now now we have AI. Okay, they good in many things, but still they not actually intelligent. Then this now I come to the second field of mathematics, but approximation theory, which is actually is the design of deep neural networks. And if you read the paper by Phút that I said, and then actually the design of neural networks you see in computer science now, they actually very much like this theory, which they developed in 1960s. So it's at the same time with the first workable neural networks. At that time, neural networks were very simple. Just produce something, just like what in this paper article that I said before, so they just that simple. The reasoning because at that time we don't have much data, and the computers are not very strong. And nowadays we have too much data, many data. For example, now 1 year old could create a lot of data. But just take the smartphone and then you take pictures, so you have a lot of data now. Because and then this is the picture of the problem in classical statistics. I said before that you try to pick, you have this the blue ones your data, and you try to fit it in some curves. And this is maybe some degrees, and this is the best one that you can get. Let's see. Okay. Now let's come back to linear regression. You have data and you try to fit it into a line. So this is the classical machine learning, classical statistics. It's still useful for many data, but it's not useful in general, because possible this problem of classify in a count or not a count, you linear regression not good enough. And not just linear regression, but you also use polynomial interpolation. You use higher degrees, but still it's good, it's better, but still not good enough. Instead of this and later you will understand why polynomial is not good enough for general purpose. And then after that we have many the functions, and they not polynomials. For example, exponential functions, and even value is piecewise linear function. It's max 0t, and it's close to be polynomial, but it's not polynomial. And actually, experiments show that you use this value is also good. And then max pool is you just take maximum of a set of numbers. And maybe I think for example our friends actually we cannot do very complicated calculations. For example, even just take square of a number. If that number is not an integer, it's not easy to compute for us. So maybe that's the reason why, even if just using value or maximum, maybe it's good enough. That's the conjecture. I don't know. And also, even if you have no linear functions, then when you actually use it, you will use like gradients or Hessians. And what are gradient Hessian? Gradient Hessian is kind of you are trying to approximate the function by linear operators near the point. If you use the possible Taylor's expansion, and that's why linear algebra is important again. Before we saw that linear algebra is important in possible the output by Google. And now and later, okay, so linear algebra actually it's used a lot, and I will explain more later when we come to linear algebra. And now, okay, so this is what I said. This will explain why we want the function not a polynomial. And it's in the paper that I listed before, input paper, in the reference that it's called the universal approximation theorem. And now for simple, you just let's say you have function f from some Rm to R, so the real value function. And then this theorem said that okay, you fix the function sigma which is not continuous and not a polynomial, like for the radio. Radio is not polynomial. Any continuous function can be approximated on compact set. So usually you look at compact set and you ask whether you can approximate this function by this sum di sigma li x plus theta I. So let me explain. So x is in Rm, li is a matrix, and in this case, okay, you want sigma yes, and sigma is just one variable, and it goes to one dimension. So what does it mean to like sigma apply to a vector? It just means that okay, sigma apply to x, y, it just sigma x and sigma y. And the claim is that any function like this can be approximated by this kind of function, the sum ci sigma lix plus theta I. And if you think about kind of neural networks, then here you say that okay, you have two maybe again 3 or yeah input layer is x, give you x, and then you apply lix plus theta I, so this another layer, and then you apply sigma, and then you sum sigma and some constants. So it say that you can approximate any function by a combination of kind of a neural network with the. It depends on how you count it, but it's maybe 1 or 2 layers. Yeah. So this is the theorem.
In this case, the sigma is one variable.
One variable. Yeah. It's sigma from x from R to R. Possible sigma is sigma function. Always value or something. And sigma function is kind of a one-dimensional case of the softmax function that I said before, and you use it when you want to classify with only 2 categories. First of all, you want to know if a meter has a cut or doesn't have a cut. So you can think about this like represent the property that your meter has a cut inside. But if you have more categories, then it's better to use the one hot vector and use softmax function. Yeah. So this is the theorem. So I said that you could use like neural networks with 1 or 2 with 2 layers to approximate anything. So it sounds good, but actually in practice, it's not good because maybe this is the theorem, but in the practice it depends also on data, and also the number n may be very big, and Actually, people found that by experiments, if you use more layers, it's better than use only 2 layers. Even the theorem said that okay, 2 layers is good enough, but in practice, more layers better. Maybe not too much, but too many. But if you are more than 2, then it's better.
In general, we have a general form for that theorem. Like if we want to approximate the function from Rn to R, do we have some kind of theorem like that?
This is called a function from Rn to R. Yeah, this theorem is called, and then you can and then you can apply to any if you have more like Rn to Rn, you can use any more coordinates and yeah, this function is applied to any kind of like Rn to Rm. Yes. Okay. Other questions? Okay, so now we can come to deep neural networks. Yeah, so one way to design that you could have many of such things. You put them together, and you can change the dimensions. So you have some layers, and then you apply sigma k. Sigma k is a one dimensional function, and you already know it. So and then you put many things. You compose them together, and in similarity to biology, so people say that the layer has a neurons if that layer actually Rn. So if we look at the picture of deep neural network, you can think about this. So you have your input layer, and then you have many other layers like this. And then first of all, if this you go like first of all you want to classify like 3 particles. So the last one would be 3 dimensions. And if you go from bigger, so maybe it could be you have the number of cells, so maybe you have and then pass I think 3 for the colors. And then you could go any kind of dimension you have, like first of all, this could be R1 red. And this number 1 red is called the number of neurons. It's just to be like in similarity to biology. So okay, so we can think about like a neural network, like we compose these things so together. So the xk is also x here, and then if you go here, it's the x1, and go here x2 and so on. Xk. So xk is the variable on the layer k, on the k layer. And sigma k are nonlinear function, and real from real to real, and you already knew you knew about them. And LK matrices and theta k are vectors, and these are not known because these are what you want to choose them so that they are they best fit your data. So let's see. So what in possible if you go from like R1 red. So this possibility of 50. So what would be R of what would be L and what would be theta? So theta will be vector in here. So theta is in R50. And L is a linear map from R100 to R50. So it has let's see, it has 50 rows and 100 columns. And at beginning, you don't choose L and theta because you don't know what is good. So you just have them like parameters. So then how many parameters you have? So in L you have 50 times 100. So 50, so 5,000. And then for theta you have 50. So in total you have 5,050 layer parameters for this to count from here to here. Now, if you have more, like from here to here, so you just add them together, and then you have the number, the total number of parameters for your neural network. And actually, this idea is that we should not fix LK and theta k, but we should try to go from some random values for them and try to get better values later. Actually, it came from Biss and Makulov in that article. So actually they have this idea that the neurons are beginning neurons in our brain. So the actual neurons at beginning they don't need to be like already good. They just start from something random, and then after you learn, then they will convert to something with can do the work you like, you want to do. And this actually this the same thing that people do in deep neural networks, in deep learning.
Usually, I'm a bit confused about NK.
First of all, I just call it the
next stage, the data in the input.
So the X is the input, and then if you come to this the first layer, so layer 1, so you will have first of all 1,000, then X1 will be a thing in here. X equal to X1 and X1 equal to X2.
So X1 is obtained by applying a function that make it scale on the X.
Something like this. Of course, later you could do many more, but at the beginning, just for single design, you can do like this. You apply a linear map to X, and then you add theta, and then you apply nonlinear function sigma. So that's you get X1. And then from X1, you go to X2, the same thing. You apply another linear map to X1, and then you add theta 1, and then you apply sigma 1, and so on. And then if you, so each of these are really simple, but if you apply many times, then you get a very complicated function. Yes, and then actually this idea of random in this, yeah, like I said, many things that we see now actually they were people knew before, but they couldn't do it because they didn't have enough technology. Even many of the possible LLM, large language model, many of them, the theories actually they was before. So people when they studied about language, so they also have this type of thing. They couldn't do calculations. And now with the very good computers, now they can put these things into calculations. And then maybe there's a difference between universal approximation theorem and the design of deep neural network. So what happens is this. What happens is this in universal approximation theorem. You have sum of C J sigma L J X plus E J. In the deep neural network, when you use data, you don't have this sequence, right? You don't have. But then in deep neural networks, you have more layers. Yeah. If you look at the yeah, okay. So in deep neural networks, you don't have this CJ. And also there are many other differences which I will come later. Then yeah. So okay, so we see that universal approximation theorem said okay, it's very good. You only need 2 layers. You can approximate everything, but in practice you need to use more layers. And then it means that actually if whatever theory you have, you need to test with the reality to see what is good. Yeah, because it's not just theory. Theory is not theory is good, but when you apply, then maybe you need to modify. You need to do a lot of things. And let's see. Yeah, we had one. So I can take we can take the rest for 10 minutes, and we can come back at 10. Okay. Chắc 15 phút hay là approximation thì cũng có những cách tiếp cận và đa cái approximation theorem rồi còn nhóm nguyên năng y cũng có những tiếp cận của approximation theo những khác theo kiểu ấy là theo kiểu lâu hay là flow flow thì thực ra là flow anh cũng có giải thích ở đây cái sau này flow thì thực ra nó đến từ cái ý